Hello, this is Bukanya Siraje taking you into chemical bonding in our chemistry made simple. In this video, we are going to look at ionic bonding, covalent bonding. We also look at dative bonding or the coordinate bonding and what we call the metallic bonding. Let us start. Well, an ionic bond is one whereby a non-metal bonds to a metal. So that's why you're calling an ionic bonding, whereby you have one is losing electrons and the other is gaining electrons. So that is what you're going to call an ionic bond or an electrovalent bond. We are giving an example here of sodium and chlorine. Sodium has 1 electron in the last shell and chlorine has 7 electrons in the last shell. So which means that sodium can easily give away the electrons to the chlorine and becomes positive charged, and then the chloride gains the electron to become negatively charged. So that's why you're calling it an ionic bond, as you see here. Okay, from our physics, we know that like poles repel and unlike poles attract. So we know that always those that repel push away. There are forces that push them away, and those that attract, the forces that pulling them together. So this happens when you look at sodium and chlorine. The sodium ion is positively charged and the chloride ion is negatively charged. So they attract due to that electrostatic force created is the one that we have between the ion bonds. Due to the transfer of electrons, we shall have that happening. So basically, that's what happens in electrovalent bonding, or we can say ionic bonding. With the covalent bonding occurs mostly in nanometals. As we said, the other one was occurring in metals and is occurring in nanometals. If we have, for example, sharing of electrons, whereby if you have hydrogen and hydrogen, they both have only 1 electron in the last shell. So they all want to attain a stable electron configuration. That is, if they get the 2 electrons in one shell, they'll get what we call a duplet. So which means that the H and H will be the same type of element, so they create a non-polar the kind of bond, non-polar covalent bond. Yet when you looked at let me say hydrogen and the fluorine, they can't have such non-polar, because hydrogen can now be positively charged and the fluoride negatively charged. Well, they're not the same. Hydrogen will now just lose the electron and the fluoride will gain it. So which means they form a polar covalent bond because they are not going to be of the same type. So that is something that we can see in this illustration. If we look at a small exercise here that I can give you, where I look at a bond between magnesium oxide, MgO, chlorine and chlorine, sodium and fluorine, hydrogen and bromine, the iodide and the bromide. They will tend to also want you can do it as an exercise, as a quiz, to find out which kind of bond is formed between them, whether they are ionic, non-polar, or they are polar. So we can use the table which gives the difference in their ENs. If you find that they have their EN that is let me say more than 0.5, the difference is 0.5, then we can classify them accordingly. So you look at the EN of each of them and see, and then we can get the difference between the ENs, and then you tell. If it is more, then you can tell that it is polar. If it is less, then you can say it's non-polar. That is something that you're going to investigate in this. But if you can see that it is a metal with a non-metal, at times you can see that it is obvious, and you say ionic bonding. And if you see a non-metal and non-metal, you can even also see that it's obviously a covalent bond. So that's something we want to investigate and see with these illustrations. For magnesium oxide, it is ionic, as we see, because magnesium is a metal and the oxide is a non-metal, so automatically it's ionic. You can see the magnesium loses 2 electrons, so it has a positive charge of 2, and the oxygen gains 2 electrons, it has a negative charge of 2. So it is going to be an ionic bond formed between them. But if you look at the 2 atoms of chlorine, we have a different state, because now they are all non-metals. So it's going to be non-polar. If you want to investigate their EN or their electronegativity, then you can see that it will automatically be less than 0.5, and that means it is non-polar. If you look at sodium and fluorine, sodium fluoride, sodium is a metal and the fluorine is a non-metal. So automatically you're going to form an ionic compound. That is that. If you go to hydrogen bromide, automatically you look at their EN. The EN here, the difference between their EN is 0.5 if you try to get it from the table, because so being greater than 0.5 to 0.7, that means automatically we say it is a polar covalent bond, because for it to be a non-polar covalent bond, it must be less than 0.5. So that's something you are going to investigate here. For hydrogen bromide, okay, to get that 0.7, you're saying if the hydrogen is 2.1 and then the bromine is 2.8, so when you subtract, the difference is going to be 0.7. So that is it. That's how you get it. You can do the same thing also to the hydrogen bromide. The iodine, it's 2.5 and the bromide is 2.8. When you subtract, you get 0.3. So automatically you say it is going to be less than 0.5, which is going to also be a non-polar covalent bond. You can do more exercises like on CH, OH, FF, and CAS. So, and find out. If you look at CH, it's going to be C is carbon is 2.5 and hydrogen is 2.1. When you subtract, it is 0.4. So it's going to be non-polar. You can try also with O and H. Oxygen is 3.5 and hydrogen is 2.1. When you subtract, you get a value which means that value is bigger than 0.5. So it's going to be a polar covalent bond. You can try also with F and F. It's automatically that one is non-polar. Then calcium sulfide or CaS is a metal and a non-metal, so it's going to be ionic. So those are some of the investigations you can do, and you find that they give you such an expression for what we investigate about the covalent bonds in this kind of exercise. So we can move on and look at what we call the now, a dative bond, also known as a coordinate bond, is a type of covalent bond formed when electron pair that is shared comes from only one atom. Example, formation of a dative bond in ammonium ion. You have all the hydrogen atom being stable in the ammonia, because the ammonia molecule, because they have all attained the duplet. They have 2 electrons in the last shell. But now there is a lone pair of electron that is in that molecule that is left on that nitrogen. So it is going to be shared with hydrogen ion that is unstable, forming the ammonium ion. So which means that ammonia molecule plus the hydrogen ion, you're going to get the ammonium ion. That's the first example you can look at. In another example, you can also look at formation of a dative bond in hydroxonium ion. So if you have the water molecule, the hydrogen in it are all stable because they all have 2 electrons in the shell, but there's a lone pair that remains on that oxygen. So which means that that lone pair is going to be shared with the unstable hydrogen ion, so forming the dative bond. So which means hydrogen and the water molecule plus the hydrogen ion, you're going to get the hydroxonium ion. So that is how we can form the dative bond. So those are some good examples. There are many other examples you can look at that can help you to illustrate this. Now, when we move on to metallic bonding, metallic bonding is a type of bond formed when the metals bond to metals. We have seen the other examples where metals are bonded to non-metals, forming ionic bonds, non-metals forming the covalent bonds. So the solid metal consists of giant structure of atoms arranged in a regular pattern. So you find that this metal is surrounded by electrons in the outermost shell, which give up their outermost electrons, share them with all other atoms in the metal, meaning that all the atoms become all positive ions because they all move the negative electrode. This is because electrons are free to move, are called delocalized electrons. Now will be a lot of electrostatic attraction forces. The forces of attraction which hold everything together in a regular structure of this metallic bonding. So it is due to that. And because of negative ions move to the negative electrodes, it gives that structure of the metal. It gives the overall strength of the metal. That's why you find that they have the property of having a high melting point and boiling point. They're solids at room temperature. They are good conductors of electricity and heat because of the localized electrons. They carry electricity, electrical current, or thermal energy. Metals are malleable. They can be turned into different shapes without breaking because of that thin sheet. They can easily slide on one another. Because of the strong structure, the layers can slide on one another. So they are thin. That's for pure metals. If you want to make the metal harder, then we form what we call alloys. That means those which consist of two or more elements. And they are formed by mixing together two different metals, or you can even add a non-metal. And they stop sliding over one another because now they are becoming harder than the pure metal. Ig steel, it contains carbon, chromium, manganese, all vanadium, and then it can become stronger. We can use it to make cars, planes, and so on. So that happens with those metals, basically. So you can see that the recap of what you have discussed, that the ionic bonding is found between metals and non-metals. Then covalent bonds are formed between non-metals, and then now you see the metals are formed between, metallic bonding is found between metals and metals. So basically, that's a small recap that we can look at. So we can meet in another video. Don't forget to subscribe to this channel so that you can get more ideas in chemistry. Thank you very much for watching. We can meet in another video. Bye bye for now. Hello, this is Bukanya Siraje taking you